Okay, this is the high-level review or the summary of the analysis in R that was done previously. It should be part of this playlist as well. This is for Small Bank USA, and we're going to look at the individual credit worthiness of new applications. So the bank has seen an increase of 73%, and it's gotten 250 new applications. The current manual process may be too long, and the bank may end up losing customers. So we got to look at a statistical learning approach to balance this human-machine decision-making process. We have the following information available. It's essentially two files. One is credit data training, and the other is customers to score. For the credit data training, we have 500 records, complete loan cycle from beginning to end. Not necessarily all successful loans, but we have beginning and end cycle information, and 250 records for the customers to score. Available information, we have the following independent variables. There's some issue with some of this data, but it's fairly consistent. Hardly any data is perfect. Some issues, but it's in-house, and we've seen a lot worse. And for whatever needs to get done, we can defer pre-processing until much later on in the process. Outcome for training and testing. We have our credit application result. Again, since it's end-to-end, we have that information. And we have our two classes of credit-worthy or non-credit-worthy, which is going to spill over into our new applicants for their predicted classification. And we're going to set that cutoff at 0.5, so credit-worthy needs to be higher at 0.5. Clearly this is a classification problem. Again, in-house data fairly clean, but pre-processing can tidy up some of it a bit further. So we've got quite a few statistical methods to pick from. So well, let's just pick three. And when we look at the interpretability and flexibility diagram, we're picking three. We're going to pick one top left corner, one in the bottom right, and something in the middle. And when we do that for classification, we end up with logistic regression somewhere near least squares, random forest somewhere below the trees, and then a support vector machine near the bottom right. Logistic regression, it almost seems to be a default if you have a classification problem, since it seems to be the equivalent of, so least squares is to numeric what logistic regression is to binary classification, I suppose. But I think it should be a good first choice for most. A random forest, so somewhat below trees or at trees. It's random forest is a collection of trees, and its intent is basically to decorrelate trees to reduce the variance, and often does quite well. Last is our support vector machines. So from a computer science perspective, this is one of those instances where the models are moving away from probability scores or probability considerations, and support vector machines, they take instead a different approach. It's a hyperplane approach. Specifically, this is about hyperplane separation, and the goal or the end result is to find that one hyperplane that makes the biggest gap between two classes. So again, we'll see which one of these three serves us best. Overall framework, key packages is going to be the Tidymodels and workflows. We're going to do a train and test, and we're going to split it at 70-30. We'll do tenfold cross-validation. And within cross-validation, we can address the class imbalance, because what we will do here is we're going to stratify this split, which is automatically going to be done by the software. So yes, 70-30, but the 70-30 split will be properly balanced between the credit-worthy and non-credit-worthy, because we have more of creditworthy. Pre-processing in general, need to consider dummy variables, imputation, decorrelation, normalization, and transformation. And we're going to accomplish most of this. Now we're actually going to accomplish everything of this, not necessarily all of these considerations in every model, but just generally speaking, we do this with step X functions. For instance, support vector machines, they are working now in a hyperspace or hyperplane, so distance is important, so we need to normalize. So step normalize all predictors. One of our fields, age years, has a couple of missing values, not too many. I think it's maybe less than half a dozen. So we will do a step impute median on age years. And there are other step X functions to pre-process our data. Model parameters, so of our 3 parameters, these are the engines that we're going to set using the Tidymodels framework. And we have some other parameters, mostly question marks, which are going to be auto-tuned in the tuning settings. The only one we're actually going to set is mtry. Mtry is going to be set to the square root of the column, since that seems to be a really good way to start off. Let's see, for model training, we are going to, again, the Tidymodels framework, we are going to define the model, the recipe, the workflow, and then a 25 parameter tuning grid. We're going to conduct our pre-processing using Tidymodels recommendations, and we're going to set the auto-tuning parameter selection for each model to rock AOC, right? Receiver operator characteristics / area under the curve. So what this actually is going to end up doing is it's going to, for each model, or for the logistic regression, for instance, we're going to come up with a 25 parameter tuning grid. The software is going to automatically pick which one of these 25 models is the best fit for the logistic regression using ROC AOC as its metric. And it's going to do that for the logistic regression, it's going to do it for the random forest, and it's going to do it for the support vector machine. So technically you could say we're basically going to test a total of 75 models, and of those 75 we're going to pick 3, but it's really 25 of each of the 3 main models, and then picking the winner, which we're then going to move into the testing, and then we're going to put those 3 up against each other, and we're going to select the best one, from which we will then use that final model to do the prediction on, to get our 250 new record classifications. So here's the training results using our metrics of AUC and accuracy. We can see here that random forest did well in both metrics. It's in green, followed by the blue support vector, and then the logistic. And of course, with this interpretation, we want to be as far left and high as possible, because what this basically means is we are, like, if we were in this area here, we are correctly identifying our ones without misclassifying zeros as ones. That's what this means over here. So getting as many correct without misclassifying zeros as ones. Of course, training is important, but not as important as the testing results. So now we're doing this on the, so this was on the training data, we're doing this on the test data, and we see on new data, how did the model do? Well, things are converging a little bit, and I think, let's see here, 70. So overall, we did a little bit better on our testing data. Seems like we have a fairly good model, because our testing results are quite well, but things are converging. Probably a bit difficult to visually look at it, but looking at it numerically, we can see that our random forest is doing quite well. If not, it's doing better in both metrics. So when we predict for our new applicants, then this is what we end up with. We have an Excel file, and looking at the top 5, we see that customer ID 353 considered creditworthy at 0.97 probability, and then below that we have kind of a split between where we see that 0.5 split between creditworthy and non-creditworthy. So customer 357 right at the edge at 0.51, and credit customer ID 495 non-creditworthy at 0.496. So, and when we do this for all records, for all 250 records, we end up with something like this: 208 creditworthy customers and 42 considered non-creditworthy. But we can further split this up into deciles. Alright, so we can take those 208, and see how well they rank in these 5 decile percentages: 50 to 60, 60 to 70, 70 to 80, etc., etc. And lastly, we have our variable importance plot. We took the top 10, and now just looking at the top 5 of that is credit amount, duration of credit month, age years, account balance, and payment status of previous credit. This is what the model's opinion, quote unquote, is. So in summary, we use the Tidymodels and workflows framework to create a very flexible and interpretable classification algorithm. We ended up with the random forest, and we have a general idea thanks to the variable importance plot what some of these important factors are distinguishing creditworthiness and non-creditworthiness. Potential future work is to potentially look at confusion matrices, because we can then begin to measure specific areas of accuracy, things such as sensitivity, specificity, but again, potential future work. Okay, that's the higher level overview or summary of the creditworthiness analysis. Thank you.